But you're still muted. Maybe you switch on your microphone.
Okay, so do you hear me now?
Yes.
Thanks, Eva, and thanks for inviting me to speak about our work. And what I want to talk about today is our experiments with carbon nanotubes. I'm going to talk about two types of experiment. The first one would be about doing nanomechanics and interaction between electrons and mechanical motion. And the second part I want to focus on is a new concept, which is very simple to make a charge qubit. So you know that there are design charge qubit in many forms, and there are very natural qubits that are based on natural atoms. I want to show you that by controlling wave function in an artificial atom in nanotube, we can create a new type of charge qubit, which we call atomic-like one, that has many benefits of control and coupling. So, okay, so the work is based on this system, which is a very clean nanotube placed on a piano of gates. And this system is based on a technology that we developed now 8 years ago that allows us to nano-assemble nanotubes on very complex circuits and still maintain the pristine electronic properties of the nanotube. So the idea is to separate the two hard parts, grow the nanotube on one chip, make the complex circuit that you want to connect to it on another chip, then bring these two together using nano piezo motors. You bring the chip very gently into the nanotube, and once you touch it, you can detect the nanotube electrically. Once you have electrical current that you can measure, you can ask all the questions you want to know about the nanotube. Is it a semiconductor or a metal? Is it clean? What's the mechanical Q factor, and so on. And if you don't like it, you just disconnect from the nanotube and go to another nanotube and another nanotube. And since we have many trenches, we can deterministically find the perfect nanotube that will make our device. When we have that, we just pass current between pairs of contacts here, cut the nanotube, retract, and we have a very nice, clean device. And with these kind of devices, we can do different things. Two that I'm going to talk about today are nano-mechanics and using these as very sensitive scanning probes. So if you have a piano of gates, you in fact can control the relevant degrees of freedom of the electron along the nanotube. So by electrostatically inducing potentials, for example, potential barriers, you create barriers for the electrons to go through, and isolate potential wells, which are effectively quantum dots for the electrons to live on the nanotube. We can also populate them with whatever number of electrons that we want. With the gates, we can add RF signals, which will drive our nanotube into motion, either in the first mechanical mode, second mechanical mode, and so on. And finally, by the electric field that we apply on the gates, we create a coupling, an electron-phonon coupling between the mechanical motion of the nanotube and the electrical occupation of these quantum dots. And maybe the best and first demonstration of the strong coupling between charge and mechanics was done in Barcelona and in Delft. And here you see an example from our experiment, where what happens is that when electrons are allowed to go into a quantum dot, basically near a Coulomb blockade peak, where the charge is allowed to fluctuate, the frequency of the mechanical resonator is also softened. And the reason is the same thing you probably know from an effect which is called the optical spring. Basically, if the electron is applying force which is correlated with the mechanical motion, you can get a shift in the spring constant of the mechanical system. So this is a nice coupling between these two systems, and with this extended system, we can take it further and play with it more. So for one simple and nice example is that we can choose where to put our quantum dot. And if we move the quantum dot from place to place, we see that the coupling is weak and then stronger and stronger and then getting weaker and weaker. And you can see that we effectively control the electron phonon coupling and at the same time image the mechanical mode change. But we can also go to more complicated system than a single quantum dot. The next one in complexity is a double quantum dot. And here we can control the relevant parameters. So we can control the height of the tunneling barriers, and we can control the number of electrons. If we measure transport through a double dot like this is something which you are maybe familiar with. It looks like this, and honeycomb diagram where you get transport only at the vertices of this honeycomb. And now to measure the mechanics in this system, we found that it's nicer to make our detection scheme a bit more intricate and go to a time domain scheme. So then let me show you the idea. The idea is the following. It's a pump probe scheme. We start by putting a pump signal on a gate, which drives the nanotube into motion. The nanotube amplitude is ringing up, and then we turn off all the voltages. And at this pre-evolution time, the nanotube is ringing down slowly. Then after some probe time, we turn on the probe, which is just another AC on the source. And this signal mixes together with the remaining vibration on the nanotube. It does heterodyne mixing to give a quasi-DC signal at the output, as you see here. So effectively, this mixing probes the amplitude of the nanotube vibration. If we wait more time, we will probe a smaller amplitude. So this is nice. We can measure how the amplitude decays in time, which means that we can measure the mechanical dissipation. But also, since we control the phase of this probe signal, we always start it with 0. If we shift it at half a phase, we will get a negative output signal, which means that we are also sensitive to the phase of the oscillation. So at the same time, we can measure also the frequency. We can follow the phase of the signal. And this is an example where you see that by this method, you can measure the ring down of a nanotube oscillator. Now, nanotubes oscillators are very nice in the sense that they are very simple. You use one object, the nanotube, both as the mechanical oscillator and also as the detector to detect it. You measure the transport through the nanotube. It is very sensitive for measuring the mechanical motion. But this is also the Achilles heel of the system, because if, for example, you have a situation where you don't have good transport, then it's very hard to measure the mechanical motion. And what I want to show you is that there is a nice way around it where you can actually measure electronic states even when the system is insulating. And the idea is that, in fact, you need the conductance through the nanotube not all the way. You need it only for actuating the system and for detecting. During the experiment, the actual experiment where the nanotube rings down, you don't need the nanotube to be conducting at all. So what we can do is a slightly more advanced scheme where we start by actuating the nanotube motion at a place here where we have transport in the double dot phase diagram. Then for the next stage, we move to any place in the phase diagram. The nanotube can be insulating, it can be conducting, it doesn't matter. We let it do free evolution there, and then we go back to the conducting point to do the measurement. And you can see that, for example, a double quantum dot is a system that conducts, but at very few points in the phase diagram. So we don't have, in transport, we don't have nice detection, nice eyes to see what's going on with the double dot. But in fact, if we do the measurement that I just showed you, that goes into a place in the phase diagram and it goes back and plot the mechanical signal, we see that both the frequency shift and the dissipation have much, much more structure. And if we zoom in on one vertex like this, we can identify that this line is a line that corresponds to transition of an electron across the right barrier. This line corresponds to transition across the left barrier, and this one across the center. And you can see that to get transport through a structure like this, you need all these transitions to be in resonance, but mechanics doesn't care about it. It can interact with each one of these independently, so it can measure each one of these independently. So this is a measurement done with the first mode of oscillation in the nanotube. If we do the same thing with the second mode of oscillation, we get a pattern that looks somewhat different. And the reason is also simple. The reason is that in the first mode of oscillation, the movement is symmetric of the two states. So the primary mode of electron going in and out is through the side barriers. Whereas in the second mode, the most dominant mechanism of electron movement is actually a slashing of the electron between the two dots. And this is something nice because it tells you that you can even probe an internal degree of freedom in the system that does not talk with the lids. And in fact, we can push it slightly more to extreme and ask whether we can measure it when the system is completely disconnected from the environment. So this is the experiment. We can start with a situation like this where the barriers are not super strong, and then close one barrier, we can see that one line disappears, close another barrier, another line disappears. If we close the other barrier, the two barriers, we can see that we can still measure the electron-phonon coupling, but now it's coupling between a system that is sitting on the nanotube, an electronic system, completely isolated from the environment, and still we can see very nicely its interaction with the mechanical motion. So this is a very nice starting point. In a sense, you can think that this can be a segue to create interactions between mechanical motion, let's say, of the second mode of a nanotube, and a charged qubit that slashes an electron back and forth between two wells. And in fact, this kind of charged qubit is very, very popular. Many people, you can see here a list of names of people who worked on charged qubits in this structure of double quantum dot. It's very simple to control and understand. It has a very nice wave function structure, a dipole that is very strong. But it turns out that in all the system, it's also very challenging because this kind of charged qubit is sensitive, very strongly sensitive to the environment and noise, charged noise in the environment. So what we wanted to do is to go to a different place or think of a different qubit that would still be very locally sensitive, strongly locally sensitive, but would not be susceptible to all the noises from the environment. And the idea is to simplify this kind of charged qubit, not do a double dot charged qubit, but a single dot charged qubit. Now, in a single dot, we don't have too many degrees of freedom. So how are we going to create a charged qubit? We're going to use the wave function, the individual wave function of this artificial atom that we are creating here. So that's the part that I want to show you now. How can we create a qubit out of wave functions in a nanotube? So for this, I need to do a simple regression and go back to the basic physics of what are the wave function in a carbon nanotube. And before doing that, there was another strong motivation on our side to create this kind of qubit on a single quantum dot, because the thing that we have been doing lately is to use single quantum dot as very sensitive scanning detectors of electric field. The idea is to use them as a single electron transistor. You measure the current through this single electron transistor. This current oscillates very, very strongly as function of the potential that this dot sees. This is the Coulomb blockade oscillation, which means that if we measure current sensitively, we can detect very, very tiny potential of the order of 10 to the minus 5 or 10 to the minus 6 the charge of a single electron, which means that this is a really, really excellent detector to look and take pictures of electrons. So we use it to take pictures of electrons in different systems, even when the electrons are buried, because what we are actually measuring is the electric field that emanates from these electrons. And with the system, we could visualize different kind of quantum system. For example, in one dimension, this was a very nice method to measure fragile states like the quantum Wigner crystal and see the first picture of electrons ordered along a line. We can go to the other extreme where the interaction is strong in the quantum sense of the word, such that it changes the behavior of electrons from repulsion all the way to attraction. We can measure also electronic system in 2 dimensions. 2 recent examples we've done in magic angle graphene, where we can measure different electronic properties like the electronic compressibility, or even measure the entropy of electrons. And by this, identify new phases of these systems. And this detector is also very nice to measure what is the equivalent of transport experiment. So in a typical transport experiment, what you do is you run current through a device and you measure some voltage difference across some probes. What we do is we get rid of these probes and instead come with the scanning electric field detector and image the potential across the device such that we get a full map of what flowing electrons are doing. Where are the resistance of these flowing electrons? And with this, we can get pictures of many phenomena that are known from transport experiment, but we can see them in real space. Ballistic transport, look on electron hydrodynamics, and very recently we can get images even of beams of electrons in electron optics. So this detector of electric field is very, very nice. And the question, the reason that we want now, or the question that we want to ask is whether we can make it quantum. So this single electron transistor is a classical detector. The question if we can replace it with a qubit and get better. And there is one good example for that in magnetic field detection, which are the NV centers. There you can have a qubit that by quantum manipulation, you can have very nice detection of magnetic field. And the question if you can do the same thing for quantum detection of electric field. So let's say we want a qubit that would detect the electric field. We have 2 options, 2 categories of qubit that we can consider. There are atomic qubits, which are atomic defects. These are very nice because they are very, very small, and they have very long coherence time, but this is also their deficiency because they are so small, they don't have nice dipole moments, so they don't interact very well with the physics that you want to detect. On the other hand, you have the engineered qubits, like the double dots or the trans-muon qubits that you know, and their advantage is that they are much larger. They have much larger dipole moments, so they are very good at sensing. You can control their energy spectrum very nicely. But on the other hand, because of that, they are very sensitive to the environment and they have very short coherence time. So what we wanted to do is to find something that would combine the advantages of both and would be like an atomic qubit, but with large wave functions. So we are going to use a single quantum dot, which would be an artificial atoms, and we are going to use the wave function of this artificial atom. So let me go back and discuss the wave functions of nanotube. So the wave function of nanotube start with graphene that has Dirac electrons as its starting point, living in 2 valleys, which we call K and K prime. All in all, we have 4 flavors for the electrons, 2 for the valley and 2 for the spin. Now, if we roll it to a nanotube, 1 momentum stays untouched, and one of them, because of this rolling, becomes quantized, which means that just like Bohr-Sommerfeld quantization, so it means that out of this axis, we get only discrete value of K perpendicular, which slices 1D subbands out of this two-dimensional system. And transport, we care only about the lowest subband in the system. Now, depending on how you cut, you can get a semiconducting nanotube with a gap. You can have a metallic one without a gap. We're going to use metallic one with slight strain that opens a gap. It looks like a semiconducting nanotube, but the gap is much smaller and much more nicely behaved. Now, you can see that the perpendicular momentum of the two valleys are opposite in direction, which means that electrons in one valley are rotating clockwise around the nanotube, and electrons on the other valley are rotating counterclockwise. And this means that these two valleys have opposite and very large orbital momentum. Now, if you put a magnetic field here adds an Aronoff bomb flux and changes the quantization condition of these two momenta such that one becomes small and one becomes large. And if you plot the band structure as function, energy as function of magnetic field, you can see that for one valley, the magnetic field, in fact, decreases the band gap, like you can see here. And for the other valley, it increases the band gap. Now, if we confine the electrons along the nanotube, we quantize the electrons also there and create wave function, one-dimensional particle in a box wave functions. So instead of having continuous spectrum, we have these particle in a box stage, which are fourfold degenerate because of spin and value. At zero magnetic field, we have this fourfold degeneracy. At finite magnetic field, the split according to the orbital momentum and smaller splitting because of the spin, and each level like this split into four. And we have the same thing for the holes. Now you can see that here we have crossings between different wave functions within the nanotube, which means that in each of these crossings, we can try to realize a nice qubit. So take this crossing that I'm marking here, for example, you can see that here you have a crossing between two different wave functions. It's coming from two different valleys, so it has different orbital momentum. And in fact, here it also has the opposite spin. So you can see that the fact that there are two different wave functions gives this, if this is going to be the basis of a qubit, this would give it an electrical dipole moment. But unlike the double quantum dot, which is sensitive to electric field also in the far field, here the wave functions are both symmetric with respect to the center. So there is no dipole moment, only higher moment. So this is a very local detector of electric field, which is good both for nanomechanics and for scanning probe. So it's a good detector of electric field, but also because we have opposite moments, it might be also a good detector of magnetic field. So we can gain both these things in the same thing. So if we zoom in on a crossing like this, there is one more element which we forgot, which is the Coulomb blockade, the charging energy. If we add the charging energy, what it does, it split these peaks by a certain amount into Coulomb blockade peaks that zigzag according to the wave function that is available. This is how it looks in a measurement. A single quantum dot measured the transport, and we see this behavior very clearly. So we see the Coulomb valleys, we see the Coulomb peaks, they zigzag, but the interesting part is that we see only the zig and not the zag. Okay, the zag is missing, it's dark. And in fact, it looks like all the electrons that are living on one valley are bright and all the electrons that are living on another valley are dark. And there is a very simple and interesting reason for that, which is that the barriers that confine our quantum dot are actually the band gaps. That's how we designed these quantum dots. And if you remember, I told you that at finite magnetic field, the band gap of one valley becomes smaller and the band gap for another valley becomes larger, which means that this would have a very transparent quantum dot and this one would be very opaque. And this is nice because if this is going to be our qubit, it gives us a very simple transport-based readout mechanism one conducts and one does not conduct. So we can, by simple transport, measure the basis of this qubit. So we are going to focus around one of these vertices and go from a state with L electrons to N electron plus bright wave function like this, or dark wave function like this, and this is going to be our qubit. So a quick summary of the properties: we have a we are trying to have a qubit with different wave function that would give us electric moment, with different magnetic moments, so we'll get magnetic detection, and with different transport properties, so we can have built-in readout. Okay, so this is all kind of nice of theory or textbook. No one saw, for example, that this wave function is indeed happening in real life. So the first thing we can do is to try to image these wave function. And in fact, within the device with the piano of gates, we can do an experiment that roughly images the wave function. So the idea is very simple. Just measure the Coulomb blockade of a certain wave function with respect to all the gates together. You get a peak like this. And now add a small voltage on one of the gates. This voltage would shift the Coulomb blockade peak a bit. And this shift would be proportional to how much charge density you have above this specific gate. If we do it on different gates, we'll get different shifts. So by measuring these shifts, we can image what's the charge density at different places. Here you see the experiment, you see the peaks before and after shift. And if we do it for all the gates, we can get images like this. So this is the bright with charge density, and you can see that it's extended over the entire nanotube, whereas the localized is the dark one is nicely localized in the center. So this is very nice. We image the charge density that we think we have. Okay. So now it's time to start to play and see if this behaves like a qubit. Okay, so the experiment is going to look like this. We initialize our qubit at the Coulomb blockade of the bright peak, then run into the Coulomb valley, wait a certain amount of time, go back, measure transport. If we are still in the bright state, we will measure something. If we switch to the dark state, we will get no current. And this is what you see. If you are close to the bright state, we just see the remnants of the Coulomb blockade. But at some point, we get a very sharp suppression of the current. And if we do it as function of gate voltage and magnetic field, we get a nice diagram in which we can identify both the Coulomb blockade peak and this new narrow line feature, and that emanates from the Coulomb blockade peak, and it's easy to convince yourself that this is the line where we have a transition between the bright wave function and the dark wave function. So this is going to be our qubit transition line, and basically what happens in this experiment is that if we start from here, go short distance and go back, we're back in the bright wave function. If we go across quickly and go back, we are still in the bright wave function. But if we come here and we stay a bit, we might decay into the dark wave function. And when we go back, we just don't measure current. So this is a nice starting point for a qubit. Let me show you some initial experiment on this as a qubit. So the first thing we can measure is the T1 time of this qubit. And you see the experiment here. You can see that it's a good fraction of a microsecond. We can also do an experiment that measures the coherence time of this kind of qubit. Here you see Landau-Zehner-Stuckerberg experiment that shows you that we get nice coherence in this qubit. Still not perfect, which means that we still didn't do a coherent manipulation of this qubit. But I remind you why we wanted this qubit in the first place. We wanted it because we asked whether a quantum sensing can replace our classical sensing, our single electron transistor, and give us better electric field or magnetic field detection. So single electron transistor is currently the best detector of electric field that exists now. And if by switching to quantum sensing of electric field we improve, then we are really getting into the state of the art. So you can see that geometrically or physically, the qubit that we just implemented in the single quantum dot is exactly just like the SET detector. We just need to switch the mode of detection. So we can just use it as a qubit. And you can see already from this diagram that it can act better as a detector, because detecting electric field is actually detecting your signal along this voltage axis. You can see the Coulomb blockade is much wider, so it would be much less sensitive than a narrower line to electric field. But it would be even better if we try to detect magnetic field. Along the magnetic field, the SET is hardly sensitive, whereas because we have a large magnetic moment in the basis of our qubit, we get also a strong dependence on magnetic fields, so we can have a good detection of magnetic field. So let me just finish by showing you how it actually works as a detector. So what we did is the simplest experiment, just change as function of time the electric field and magnetic field and detect the DC component of both. So this is the result comparing the SET and qubit in electric field detection, where the SET excels. And you can see that we improve by approximately an order of magnitude over our best single electron transistors. We are down to the few hundreds of nanovolt per square root hertz, and this is really important improvement in electric field detection. But you can see that if we do DC magnetic field detection, SET doesn't give you hardly anything, but the qubit actually get nice sensitivity, which is comparable to the DC magnetic field sensitivity of NV center. So with this, I want to summarize mostly the part that I discussed about the qubits. So what I try to show you is that there is a very simple realization of a charge qubit that is easy to do in a single quantum dot of a nanotube. It's small because it's a single quantum dot. It's very simple. In fact, it doesn't need all this fanciness of many, many gates. You can have the simplest transistor with one gate, have a quantum dot, and if you follow this recipe, you will have a charge qubit. It doesn't need any extra readout device to read out the qubit state. You can really use the transport because you can get dark and bright states. It's exactly the same geometry that we use for scanning, so it's a nice scanning detector. We didn't do so far coherent manipulation of this qubit, but I showed you that already now it has a better electric field detection sensitivity than the single electron transistor, and it already has a pretty nice simultaneous DC magnetic field sensitivity. And last thing, as compared to other magnetic field sensors like SQUID or NV centers, this kind of qubit doesn't care about magnetic field. It can work at very high magnetic fields. So with this, I'm thanking you for listening, and I'll be happy to get your questions.
Well, thank you very much, Shahal, for this beautiful talk. We do have time for questions. So I see that Alex Eichler is raising hands. I'll try to, yeah, I think you're still muted.
Yes, no.
No, okay, so it's working, okay.
Okay, I thought we should try that out with the hand instead of the just the chat. Hi, Shahal, great talk, thanks a lot. This is a very impressive qubit that you describe, but I think you haven't talked about what you can do when you now use the coupling of this qubit to the mechanical motion.
Yeah.
So is this something? What is the coupling rate? What will it enable?
So we didn't do a lot about this. We just did a bit, and in fact, the best mode to couple to is the third mode of the mechanical motion. We didn't push it in this front a lot we didn't see yet strong coupling, but we mostly pushed it as a scanning detector for now. That's what we are really focusing on now. but in principle, you can imagine it has nice mechanical coupling. It's weaker than the double quantum dot to the second mode, but it looks like a direction that can work also well for mechanics.
Thanks a lot.
Okay, are there further questions? Okay, not yet. Maybe people are typing in the chat. So I'm not sure if I caught this correctly. I think you said that you need to strain the nanotube a little bit to allow you to realize the qubits. How much strain do you need for that? So
this is something that happens naturally. I mean, you cannot avoid this strain. So whenever you make a device, it's always slightly strained. And this opens a small band gap. And the small band gap is nice because it's much easier to create, to control the barriers if the energy, the height of the barriers is not huge like in semiconducting nanotubes. So it helps you to close and open barriers, which it's much harder to do with semiconducting nanotubes. So most of the clean nanotube experiment that you've seen in the literature, let's say in the last 10 years, are coming from this kind of class of nanotubes, which are small bandgap nanotubes.
Okay, thank you. I missed the fact that it was built-in strain. I was wondering how you can strain it. Okay, now we have two more questions. The first one by Christopher Moller. Thank you very much for the excellent talk. Are you planning on doing coherent manipulations? If so, what are your main hurdles?
So that was our plan originally, but now we are deviating more and more to single electron scanning of two-dimensional and one-dimensional systems. So we, just from the practical point of view, we're less focused on that. What are the hurdles? The hurdles are, as always, if you are trying to couple to a charge qubit, you are always competing against charge noise. This kind of qubit minimizes a lot of the charge noise because it doesn't couple to electric fields, only to local fields. It only has a quadrupole moment and higher moments. But you still need to control some of the properties of this qubit better. So for example, we need to be able to tune the tunneling between the two basis states better. And this is something we didn't do, but we know how to do, which is by playing with the spin direction of the qubit. So now we chose for a basis two states which have almost completely opposite spin. And this made these two states very orthogonal and the tunneling element between them, the Rabi oscillation between them, very small. So this is the main obstacle. If we can just dial in a small perpendicular field, we can control the tunneling rate between them, increase the Rabi oscillation time, and then the numbers show that this qubit would be really in the game.
Okay, I think we have a next question in the chat from Adrian.
Yeah, hi. So I unmute myself. Yeah, I have a question for the pump probe experiment. So when you change the gate voltage to go from read and measurement and back, so you also apply, there is also an electric force that is associated. Do you have to take care of do you have to worry if this force affects the ring down measurement?
It's a good question, but we measure that. So the question is, let's say you are in a, let's see, let's look on, for example, on a double dot diagram. So if you do that, if you run very quickly from a place here to a place here, if you cross lines where there is interactions between electrons and mechanics, you might have some effect. But it turns out that if you do it reasonably quickly, the effect is completely negligible. So we tested, and at the rate that we can sweep through this phase diagram, it's negligible effect at the crossing here. So you can measure the same measurement. Let's say you want to measure this, so you can go, let's say here, you want to measure here. So you can go to a quantum dot where you don't cross any line, or you can go to a position where you cross a line and you get exactly the same result. So it's fine.
Thank you.
Okay. So now we have 2 more questions in the Q&A, and I think, I dare to take them both. So the first one would be, when you change the wave function from one state to the other, is the number of electrons changing as well? Or are you just changing the nth electron from one wave function to the other?
It's an excellent question. So if I can go back to these slides, one sec. So when you have the Coulomb blockade phenomena, you have charging energy in the quantum dot that which is the largest energy in the system, and this charging energy actually limits very well the number of electrons in the dot. So whenever you are in a Coulomb blockade valley, your number is a fixed number. You can have n in this valley, n+1 in this valley, n+2, and so on. So what happens though is that you see that the line, the boundary to this valley is zigzagging. And what happens here is that at different parts of this valley, you have different wave functions that are into place. So this is exactly the place where we switch between having the added electron to be of this red wave function and added electron to be the blue wave function. So this is exactly the vertex that we used for the experiment here, that we start with n electron in the dot, and then we cross to n+1, but one time it's n plus this wave function, and one time is n plus this wave function. And we stay away, the qubit operation is away from this Coulomb blockade line. So we don't mess with the number of electrons in the dot, it's fixed. We go across this line where you are in a Coulomb blockade valley, and all that changes is the ground state, right? You go from a ground state with n+1 electron with this wave function to a ground state with this wave function.
Okay, and then maybe the last question, it's from Hao Xu. Thank you for your nice talk. How do you put semiconducting nanotubes on your designed devices? How do you promise their alignments accurately? You need to fix them on there.
Okay, so this is something we did. Okay, the slide don't want to move, but let's see. Let's see. Somehow it doesn't respond. Okay, I'll explain with the hands. So the trick is to use this nano-mechanics and electrical detection. You bring the circuit into the nanotube, and your eyes are the electrical transport. And in fact, it sounds very, you cannot see nanotube by eye, it's very small, but still with transport, you can do a lot. So for example, by the way you align your electrodes, you can measure not only the fact that you touch contacts, but if you make shorter and longer contacts, you can also control where you put it along the contact. So by very simple combinations of contact like this, we could place the nanotube with an accuracy of even 100 nanometers, or even place 2 nanotubes next to each other, each one connected to a different circuit. So just electrical detection allow you to make very accurate positioning.
Okay, since we're already a little bit over time, I think it's time to close the second talk by thanking Shahal again for the beautiful presentation. And I will start introducing our third and last speaker of today. Our third speaker is Michael Rukas from Caltech. Many of you may remember him as the organizer of the past FNS in Palm Springs.